Hello everyone, I welcome you all to Physics Wallah, and in this session we are going to talk about the next portion related to our very interesting chapter, which is redox reaction. Now in the first session we were discussing about the actual calculation of oxidation state, how you are going to define oxidation state as well as oxidation number, what is the concept of average oxidation number when you have central atoms which are multiple in number. Now it's time to talk about the next portion, which is the concept of oxidizing as well as reducing agent, then the introduction part of redox reaction. So basically this session will be more focused on the analysis of oxidizing as well as reducing agent, then some introduction part of redox reaction, and next important part is basically the balancing of redox reaction, and last part is calculation of N factor, or you can say valency factor. Okay, now let's start. If I talk about the first part, we generally know that oxidation and reduction processes are very easy in comparison to loss of electron as well as gain of electron. If I talk about a particular process which involves the loss of electron, that process is basically oxidation, and the process which involves the gain of electron, that process is basically reduction. Now the species which is undergoing the process of oxidation is going to lose the electron. So definitely that particular species has the capability to lose the electron. In the same way, that species which has the capability to gain the electron is going to gain the electron in the entire process. And always remember, the combination of oxidation as well as reduction occurs in most of the reactions. That's why we have the term which is redox reaction. So in that particular case, if I talk about any type of redox reaction, if I talk about any type of redox reaction, basically the process which involves oxidation as well as reduction, in that case there are two species which are present. First one is known as oxidizing agent, or also known as oxidant. Next part is reducing agent, also known as reductant. So basically the species which is going to reduce itself is definitely going to oxidize others, and the species which is going to oxidize itself is going to reduce other. So basically you can say, if I talk about the reducing agents, so basically those species or those type of agents which are going to reduce others, it means they are going to reduce other species. If they are going to reduce other species, it means they are going to oxidize themselves. Okay, they are going to oxidize themselves. Those species are basically known as reducing agent. I hope this part is clear. I hope this part is clear. In the same way, if I talk about the species which is oxidizing agent, so basically which is going to oxidize others and they are going to reduce themselves. Those species are basically known as oxidizing agent. I hope this part is clear. Sometimes it's very confusing. Students think that oxidizing agent means those who are going to oxidize themselves. So oxidizing agent means agent always works for somebody else. So oxidizing agent means those agents or those species which are going to oxidize others. Okay, so that is the meaning of oxidizing agent. It means in that case, let's say if I have the species which is A as well as a species which is B, A is going to reduce, A is going to lose the electrons. In that case, A is going to lose the electron and B is going to gain the electrons. B is going to gain the electrons. So in that particular process, if A is losing the electrons, let's say we have A2 negative, it is forming A and 2 electrons, and on the other hand B is gaining 2 electrons to form B2 negative. So you can see that this particular part is loss of electron, means the process is oxidation. So definitely that particular species is actually oxidizing itself. So definitely it's going to reduce other. So that species will be a reducing agent. Now in the same way, if I talk about the B is going to gain the electron, means the B is undergoing the process of reduction. It's going to oxidize others. So definitely that will be the oxidizing agent, and that's how you can deal with these particular part. Although there are certain tricks by which you can check like which species is going to be the oxidizing agent or reducing agent, but this is one of the idea. Okay, I hope this portion is clear. Just have a look at it. Okay. Now, if I talk about certain special type of oxidizing as well as reducing agent, you need to make sure that you have the entire idea about oxidizing as well as reducing agent. Keep in mind, certain species are there which can act as oxidizing as well as reducing agent, but the general idea is very easy. So, if I talk about the species which only act as an oxidizing agent, so the condition for the oxidizing agent, always remember in that case, oxidizing agent means which cannot be oxidized further, so they are going to reduce themselves. Oxidizing agent means self reduction. Self reduction is only possible when they cannot oxidize themselves. So always remember, when a particular element is present in its maximum oxidation state, definitely that will act as an oxidizing agent, because it cannot go beyond that maximum part, maximum oxidation state. So definitely it's going to reduce themselves. So always remember, in that case, oxidizing agents are basically which are going to self reduce themselves and they cannot further oxidize. It means they are already present in their maximum oxidation state. So always remember this simple trick, and you will be happy that most of the concepts related to oxidizing agent lie under this entire part. Okay. So if I talk about the reagent which is F2, F2 always reduce itself, because in case of fluorine, positive oxidation state does not exist. So definitely it's a very good oxidizing agent. You can see it's going to be converted from 0 to -1. In the same way, if I talk about O3, O3 is a good source of oxygen, because O3 when dissociates, it converts into molecular oxygen as well as nascent oxygen. Nascent oxygen is necessary for the oxidation process. So definitely it's a good oxidizing agent, and generally it converts from O3 to H2O, O3 to H2O. Okay. In the same way, if I talk about H2O2, H2O2 is the only species, H2O2 is the only species which can act as an oxidizing as well as reducing agent both. Okay. So in that case, H2O2, I'm going to talk about that particular part in disproportionation reaction. So don't worry. In this particular case, just remember H2O2 will be an oxidizing agent as well as a reducing agent. So that corresponds to H2O2 converts into H2O, which shows its oxidizing nature. Okay. KMnO4 is a very good agent, oxidizing agent. KMnO4 can work in acidic medium, in basic medium, and in almost neutral medium. So if I talk about the acidic medium, KMnO4 actually converts from Mn7 positive, which is already present in KMnO4, converts into Mn2 positive. If I talk about the next part, in solution which is slightly alkaline, or I can say almost neutral solution, it converts into MnO2. And last part, in case of highly alkaline medium, it converts into MnO4 2 negative. MnO4, sorry, MnO4 2 negative. It converts into MnO4 2 negative. Okay. That is the basic idea about the KMnO4. It's a very good oxidizing agent. In the same way, we have another agent which is K2Cr2O7. K2Cr2O7 only works in case of acidic medium and converts into Cr3 positive. Concentrate HNO3 is also a very good oxidizing agent. It generally converts into NO2. Although there are multiple products, depending upon the type of reaction which you are using, it may form ammonium ion, it may form N2O, it may form NO, it may form N2O3, it may form NO2. So that depends upon the type of reaction, but generally it's a very good oxidizing agent. Same way we have KiO3, iodate ion. So iodate generally converts into iodide in this particular reaction. So I'm going to also give you the idea how to predict the product of the reaction if you don't know anything. Okay, so don't worry. So these are the list of a few oxidizing agent. In the same way, if I talk about the next part which is related to the reducing agent, so always remember that in case of reducing agent, the idea is very easy. The idea is very simple, that we are talking about the process which involves self-oxidation. It means they cannot reduce themselves further. So basically, all the elements which are present in their minimum oxidation state. So you can say all the elements in a given compound, when they are present in their minimum oxidation state, they cannot go further beyond that particular value. So they cannot reduce themselves further. They have to oxidize themselves. So that part is basically reducing agent. So trick is you have to find out which particular species is present in its maximum minimum oxidation number. Okay. So if I talk about metals, metals generally have the tendency, because metal cannot contain negative charge. They generally contains only positive charge. They have tendency to lose the electron. It means they show always oxidation. Definitely they are good reducing agent. Definitely they are good reducing agent. If I talk about lithium, lithium is a very good reducing agent. Alkali metals are one of the example in that case. If I talk about carbon, carbon generally shows this type of behavior. It can either convert into CO or CO2. That depends upon the type of reaction. You can talk about sulfur gaseous state. Definitely it can convert into SO2. Thiosulfate, a very interesting agent, and we are going to use that particular part in multiple cases of titration, iodometry, iodimetry. Okay, in previous class also I talked about this entire part, that thiosulfate actually converts into tetrathionate, sodium thiosulfate, sodium tetrathionate. Remember, we already discussed that part in previous class. Okay, so these are the list of few reducing agent. Just like that, we have Ki. Ki is a very interesting agent. So generally it converts into I2, but it depends upon the strength of oxidizing agent. It can change its product. It can be converted into iodide ion. It can be converted into iodate ion. So that depends upon the type of reaction which you are using. Next one is oxalic acid. These two are going to be maximum used. So C2O3, C2O4, 2 negative, C2O4, 2 negative is going to be converted into CO2 in most of the reactions. Okay, and last part is H2S, which converts generally into sulfur. Okay, so these are the list of a few oxidizing as well as reducing agent. Now if I talk about the prediction, in that case, always remember, if the element is present in its maximum oxidation state, that will be oxidizing agent generally. Okay, generally if the element is present in its minimum oxidation state, definitely that will be a reducing agent. If the element is present in moderate oxidation state, then it can act as oxidizing as well as a reducing agent generally. But that also depends upon its behavior, that it will show the redox reaction or not. You cannot always say that if the element is present in its intermediate oxidation state, it will be an oxidizing or reducing agent. That depends upon its behavior, that depends upon its electrode potential. Okay, so this is the criteria which you have to understand. Now keeping this thing in mind, let's talk about H2O2. Let's talk about H2O2. Okay, H2O2. In case of H2O2, if I want to calculate the oxidation state of oxygen, so two hydrogens are there having +1 because they are connected to non-metal, plus 2x for oxygen, entire compound is neutral. So you can say X will be -1. X will be -1. It means the oxidation state of oxygen is -1. That means this compound is definitely peroxide, and that's why its name is hydrogen peroxide. Okay, well enough. Now in this particular case, we know that oxygen can go up to -2. It can go up to -2, or it can go up to 0. Generally, in certain cases with fluorine only, it can show positive oxidation state, but otherwise its oxidation state is always 0. Okay, so it can go to 0, it can go to -2, minimum and maximum, and this is intermediate. This oxidation state, now you can see, this is the intermediate oxidation state. If that is the case, it means this H2O2 can convert into a compound which is H2O. So it is converting from -1 to -2. Negative charge is increasing, it means this process is the reduction. If this process is basically the reduction process, self reduction means, in that case this will be an oxidizing agent. So whenever H2O2 acts as an oxidizing agent, it generally converts into H2O. First part. Next part, in this particular case, that H2O2 is converting into O2. O2 is native state. Native state means oxidation state is 0. In this case, -1. Now this part was minimum oxidation state, this part is maximum oxidation state, and you can see this process that -1 is converting into 0 means positive charge is increasing. You can say in that particular case this process is nothing but oxidation. Whenever H2O2 is self-oxidizing itself, that means this is the case of reducing agent. So whenever H2O2 acts as a reducing agent, it generally converts into O2. I hope this entire part is clear. So this is the basic trick related to H2O2 part. Okay, I hope this part is clear. Just have a look at it. Just have a look at it. Very simple analysis. Very simple analysis. Okay, now let's talk about a simple question. MnO4 negative, which is potassium permanganate, is a good oxidizing agent in different medium, changing to Mn2 positive, MnO4 2 negative, MnO2 and Mn2O3. Changes in the oxidation number respectively are. So it's a very simple calculation. So you know, in first case, this MnO4 negative is converting into Mn2 positive. Okay, in this case, what is the oxidation number of Mn? You can calculate that part. That will be X plus 4 into -2. That will be equal to charge of the ion because it's an ionic species. So you can say X will be +7. That part we already know that in permanganate it is +7. So +7, and in this case you can see the charge is +2 already given. So the change in this particular case, 7 to 2, change is of 5. So you can say change is of 5. First part. Now MnO4 2 negative, can we calculate? So X plus 4 into -2, that will be equal to -2. So from that particular part I can say X will be +6. If that is the case, so Mn is present in +6. Here it was present in +7. If that is the case, from +7 to +6, change is of only 1. So in that case, change is of 5. In this case, 1. MnO2. So I can say that will be X plus 2 into -2. That will be equal to 0 because entire compound is neutral. And you can say that X will be equal to 4. So from +7 to +4, you can see the change is of 3. So 3 in this case. Last part Mn2O3, so that will be 2x because 2 Mn are there, plus 3 multiplied by -2, that will be equal to 0. You can say X will be +3 in this particular case. If it is +3, so +7 to +3, change is of 4. So that will be 5134. 5134. Yes, option number C. 5134. You can see. A very simple, very easy question. 5143. Just have a look at it. A simple calculation related to the entire part. A simple calculation. Okay. These type of questions can be asked. Definitely. Now, let's talk about the redox reactions. So we know basically redox reactions are basically those reactions in which simultaneous oxidation as well as reduction takes place. So basically those reactions in which simultaneous oxidation and reduction takes place are actually known as redox reactions. So these can be direct redox reactions or they can be indirect redox reactions. If I talk about the direct redox reactions, I can say when both oxidation and reduction reactions occurs in the same vessel. So these reactions are basically known as the direct redox reactions. But when we talk about the process of cell, generally in cell there are two compartments. In both the compartments different processes are going to occur. So generally this part corresponds to your electrolytic cell and this part corresponds to your electrochemical cell. So basically the reaction or oxidation or reduction when occurs in different chambers or different vessels, in that case those reactions are actually known as indirect redox reactions. I hope this part is clear. Very simple analysis, very simple analysis. Now, if I talk about the next portion, then we have inter as well as intramolecular redox reactions. So, intermolecular redox reactions are basically those reactions in which two species are involved and both the species are different. One species is going to oxidize and one species is going to reduce. So, that reaction is basically your intermolecular redox reaction. So, basically two substances react and one of them is oxidant and other is reductant. That particular part is actually your redox reaction, which is intermolecular, For example, let's say we are talking about the reaction of a zinc with copper sulfate. Although zinc is more reactive in comparison to copper sulfate, so it's going to displace the copper from its solution and convert into zinc sulfate and copper. So that reaction involves two different species. Now in this particular case, you can see zinc, which is present in the zero state, native state. It's going to be converted into zinc sulfate. Sulfate is -2. So you can say zinc is converted into +2. 0 to +2 increase in positive charge. That particular part is nothing but oxidation. That part is oxidation. In copper sulfate, copper will be present in +2 and it is converted into metallic copper, which is 0. So that particular portion, if you look, that part looks like the process of reduction, decrease in the positive charge. Okay, I hope this part is clear. Very simple reaction. So basically in this particular case, zinc is oxidizing itself. If a zinc is oxidizing itself, it means it is a reducing agent. And copper sulfate is actually reducing itself into copper. That will be the oxidizing agent. I hope this part is clear. Now if you want to express this entire part into two separate equations, so oxidation will be that zinc is converted into zinc 2 positive and reduction will be that copper 2 positive is converting into copper by the gain of 2 electron. Okay, so that part you can do because the sulfate ion is not going to change anything. It's a spectator ion. It's going to combine with cation or corresponding cation of copper or corresponding cation of zinc. That's it. There is no other function of this entire part. Okay, I hope this entire part is clear. So this part is basically your intermolecular redox reaction, and most of the reactions are basically intermolecular redox reactions only. Now if I talk about the next part, which is intramolecular redox reactions, so basically those reactions in which same type of compound or the elements which are present in the given compound, they are going to oxidize and they are going to reduce themselves. So that process is basically intramolecular redox reaction. So basically one element of a compound is going to be oxidized and other element of the same compound is going to be reduced. These type of reactions are very interesting. These type of reactions are pretty interesting. For example, we have ammonium dichromate. Okay, so let's talk about the analysis. NH4 twice Cr2O7, ammonium dichromate. So basically we are heating this entire compound. So there is a concept of thermal decomposition. So basically there are certain compounds which are thermally unstable. So whenever you thermally decompose something which contains hydrogen as well as oxygen, so in those type of compounds, first try to remove as much water as possible. So in this particular molecule, you can see there are 4 hydrogens, 4 to the 8 hydrogens and 7 oxygens are there. So how many water I can remove? So 8 hydrogens means 4 water molecule. 4 water molecule contains 8 hydrogens and 4 oxygen atoms. this compound actually contains the same part. So you can say that I can remove 4 H2O from this entire part. Now remaining part, 4 oxygens are already left. Remaining oxygens are 3. So Cr2O3. Next part will be Cr2O3. Last part, what is left? Only 2 nitrogens are left. It means that product will be N2. I hope this part is clear. I hope this part is clear. This corresponds to thermal decomposition type of reaction. Thermal decomposition type of reaction. Now, if you want to calculate each and everything in this particular case, let's talk about. First of all, we know that ammonium ion is NH4 positive. Ammonium ion is NH4 positive generally. So in this particular case, can you calculate the oxidation state of chromium? Yes, definitely. So we have, if I talk about the chromium, I can say that we have two ammonium ions having +1 charge, because I told you in case of complex cation or anion, you can take their oxidation number as the total charge. So NH4 positive means +1. So two ammonium ions are there, plus 2 chromium, we don't know the oxidation state, which is X, plus 7 multiplied by -2 will be equal to 0. So you can say 2x will be equal to 7 to the 14, minus 14 on that side plus 14, and plus 2 on that side minus 2. So 14 minus 2, that will be 12, and you can say x will be plus 6. And always remember, in case of dichromate, it is always plus 6. Okay, so this is plus 6. Okay, so chromium is plus 6, oxygen is -2, but we haven't talked about the NH4 positive. So in case of NH4 positive, 4 hydrogens are there having +1 charge. Then we have nitrogen, let's say, which is X, we don't know, and that will be equal to total charge of the complex, which is +1. So you can say X will be equal to -3. Okay, so nitrogen in this case is present in -3 and hydrogen is present in +1. So every compound's oxidation state is known to us. It's already known to us. Okay, now N2, which is present in native state, you can see this part will be 0. This part will be 0. Now you can see that nitrogen changes its oxidation state in this particular compound or in this reaction. From -3 to 0, it means positive charge increment. Positive charge increment means oxidation. So this process is definitely oxidation. So we have already figured out what is the oxidation process. Now Cr, in this particular case, you see chromium will be present in 3 to the 6. So -6 plus 2x will be equal to 0. So x will be +3. So I am doing it directly. So +3 for H2O, it is +1, it is -2. So you can see oxygen and hydrogen, they are same, no change in the oxidation state. But in this particular case, you can see chromium has changed from +6 to +3. It means a decrease in positive charge. That process is basically a reduction. So in the same compound, you can see oxidation as well as reduction is taking place. That part is basically intramolecular redox reaction. I hope this part is clear. Just have a look at it. Okay. Okay. Now let's try to figure out some more questions related to that particular part. Let's say I have, what can we take? Okay, let's take ammonium nitrite and let's take ammonium nitrate, and again same reaction, which is the thermal decomposition. So first of all, let's try to figure out the product in this particular case. Again, this species contains hydrogen and oxygen. 4 hydrogens are there. How many water molecules you can remove? 2 water molecules. So that will be 2H2O. Remaining part, 4 hydrogen, 2 oxygen are already left. Remaining part is N2 only. So that will be N2. Done. Next part, in case of this particular part, which is ammonium nitrate, 4 hydrogens are there. You can remove 2 water molecules, 2H2O. Now the only thing which left is 1 or 2 nitrogen and 1 oxygen. That will be N2O, and that's how you can predict the reaction. Now if I talk about this entire part, I know in this particular case we have two different ions. We have two different ions. In this case, ammonium nitrogen always has -3. In this particular case, this compound is basically NH4 positive, NO2 negative. So in case of NH4 positive, we know that nitrogen is having -3 charge, which we already calculated in the previous case. So I'm directly going to use that particular part. But we don't know about the NO2 negative ion. In that case, I can say that nitrogen is having X charge plus a 2 multiplied by -2, that will be equal to -1 of the charge. So I can say that X will be equal to +3. Interesting, very interesting. So in this case, nitrogen is present in +3. Okay, and in this case, nitrogen is present in 0. So you can see that one nitrogen is converting from -3 to 0. That process is basically nothing but oxidation. Next nitrogen is converting again from +3 to 0. That process is reduction. It's a very specific kind of reaction. So basically the reaction in which same element which is present in higher or lower oxidation state is simultaneously is going to oxidize or reduce themselves. Okay, so that is a very interesting reaction. So there is a part which is known as the disproportionation reaction, and the reverse of disproportionation is comproportionation. So this reaction is a type of comproportionation reaction. So one part is in lower oxidation state, one part is in higher oxidation state, and they are both converting into a common oxidation state. So that part corresponds to comproportionation reaction. We are going to discuss that part, don't worry, but this is one of the example, very interesting example. Okay, now the next part, again ammonium ion which is present in -3. Now what about NO3? So in this case you have NO3 negative, basically because we have ammonium ion which is NH4 positive, that should be NO3 negative. Can we calculate in this particular case? Yes, X plus 3 multiplied by -2, that will be equal to -1. So X will be +5 in this case. So in this particular case, nitrogen is present in +5 and both are converting. In case of N2O, you can calculate, we have a 2X -2 will be equal to 0, X will be equal to +1. So both are converting into +1 in this particular case. So again, a good example of comproportionation reaction. So that's how you can deal with the reactions. You can predict their product as well as you can proceed for the reaction part. Okay, I hope this entire idea is clear. Just have a look at it. Okay, nothing fancy. Everything is very easy to understand in this particular chapter. Okay. Okay, now let's talk about the next part, which is definitely disproportionation reaction, because we were talking about the comproportionation. So it's better to understand first of all what is disproportionation reaction. So disproportionation reaction are the redox reaction. These are again the redox reactions in which same element oxidize and reduce. Okay, same element oxidize as well as reduce simultaneously. Okay, for example, if I talk about the process of H2O2 generally decompose very easily. So what happens that this H2O2, we know it can oxidize, it can reduce itself. So generally what happens, this is going to convert into H2O as well as O2. So this is a very common type of reaction in case of H2O2. H2O2, oxygen is present in -1, that part we already know. In case of H2O, it's going to be converted into -2 and native state is 0. So you can see that from -1 it is converting into -2. That process is basically reduction. And this oxygen is again converting from -1 to 0. That process is oxidation. So you see, oxygen is the only element which is going to oxidize as well as reduce itself. So that process is basically disproportionation reaction. Okay, a very specific type of the reaction, a very specific type. If I'm reversing that part, that means we are talking about this reaction. This reaction will be known as comproportionation reaction. Okay, so this reaction will be known as comproportionation reaction, which is exactly the reverse part of disproportionation reaction. Are there any other examples of disproportionation? Yes, there are multiple examples of disproportionation reaction. One of the good example is KClO3. So generally KClO3 converts into KClO4 as well as KCl. In case of KClO3, Cl is present in +5 and it converts into KClO4, it means +7, and KCl, which is -1. So +5 to -1 decrease, that process is reduction. That process is reduction. From +5 to +7 means increase, that process is oxidation. And chlorine is the only species which is going to oxidize as well as which is going to reduce itself. Okay, so that part is there. Another part is P4. P4 in presence of basic medium. P4 in presence of basic medium, it generally converts into H2PO2 negative as well as PH3 phosphine. So P4, which is present in the native state, is 0. So 0 to -3 in phosphine. So this part is phosphine. This part is phosphine, a very suffocating gas. So pH3 is -3. So 0 to -3 decrease, that process is reduction. Okay. In case of this ion, which is H2PO2 negative, so basically there is a phosphoric acid, there is phosphorus acid, and there is hypophosphorus acid, and that ion is hypophosphite ion. That ion is hypophosphite. So we have hypophosphite. That ion is hypophosphite ion. Okay, and you can see from 0 to +1, it means increase. That process is basically oxidation. So simultaneous oxidation as well as reduction of a phosphorus takes place. Definitely that reaction is disproportionate reaction. I hope this part is clear. Just have a look at it. Okay, there is one more reaction which I want to mention, a very interesting reaction. So what happens when Cl2, or you can take X2, normal halogen. So in case of OH negative, it generally converts into X negative as well as XO negative. And X2, when reacts with OH negative, it also forms X negative and XO3 negative. So both reactions are there. This one is cold and dilute solution of NaOH or KOH generally, that it converts into X negative as well as XO positive. So this present in 0 converts into -1 and converts into +1. Okay, 0 to -1 decrease, the process of reduction, and 0 to +1 increase means the process of oxidation. Okay, but if I'm using hot and concentrated solution of alkali, it converts from 0 to -1 and +3. No, +5, sorry, it's going to be +5. Okay, so 0 to -1 is basically reduction, and 0 to +5 is basically oxidation. I hope this entire part is clear. So one reaction is also there, very common reaction. We are going to deal with that reaction very easily. Okay, I hope this part is clear. I hope this entire part is clear. Just have a look at it. Okay, now in the same way, if I talk about a very interesting question, white phosphorus on reaction with NaOH gives a pH 3 as one of the product. This is a type of, so in this case P which is present in its native form is converting into -3 of pH 3, and in this case it is converting into +1. So you know this type of reaction is a very common example of disproportionation reaction. So the answer will be disproportionation reaction. Okay. Which ordering of compounds is according to decreasing order of their oxidation state of nitrogen? Okay, so basically we have first compound which is HNO3. In case of HNO3, we have one hydrogen plus nitrogen which is X plus 3 oxygen having -2 charge. Overall compound is neutral. So X will be +5 in this case. Okay, first part. Next compound is we have NO. So in case of NO, X -2 will be equal to 0. X will be +2. Then we have N2. So X will be 0 in this particular case. Native state. Okay. N2 is native state. And last part is NH4Cl. So in case of NH4Cl, we can say nitrogen is X plus 4 into +1 for hydrogen plus -1 for chlorine, and entire compound is neutral which is equal to 0. So 4 minus 1 is +3. X will be equal to -3. X will be equal to -3. So it should be decreasing order should be HNO3, NO, N2 and NH4Cl. Option number B. Option number B. So +5, +2, 0 and -3. That will be the decreasing order of oxidation state. Okay. I hope this part is clear. I hope this part is clear. Just have a look at it. Okay. Now let's talk about the next part, which is a very interesting portion, that is the balancing of redox reaction. This part corresponds to balancing of redox reaction. So if I talk about the balancing of redox reaction, generally there are two methods. First one is known as ion electron method, and second one is known as oxidation number method. Okay, first one is ion electron method, second one is oxidation number method. If you ask me which one I should prefer, definitely I prefer oxidation number method because it's very easy, it's very convenient, and it will not take more than 30 seconds to balance the reaction. But the one thing which is required is the calculation of n factor in that particular case. Then only you will get to know how to balance this reaction. But first of all, we have to understand what is actually ion electron method, because that is the proper method for the balancing part. So first of all, if you look at the redox type reaction, write down the redox reaction in ionic form. First of all, try to figure out the ionic form of the equation and try to write down the ionic form. Now split the redox reaction in two equal halves. First one will be the oxidation reaction and next one will be reduction reaction. So these two steps are pretty much compulsory in case of ion electron method. In oxidation number method this is not required, but yeah, in ion electron method it is required. So you have to split the reaction into two parts and then you start the balancing of the reaction. Now balance the atoms other than hydrogen and oxygen for each half reaction using simple multiples. So always remember a simple principle which is AOHC. First of all, try to balance all the atoms other than oxygen and hydrogen. Okay, next part will be balance oxygen, then balance hydrogen, and last part balance charge. Okay, always remember that the balancing of oxygen and hydrogen depends upon the medium, which can be acidic or basic. Balancing of charge always occurs with addition of electrons. So these are few things which you should know. I am just giving you a very simple trick, which is AOHC. Always remember AOHC. Okay. Now balance the atoms other than oxygen and hydrogen for each half reaction using simple multiples. Okay, done, done. Now whenever we talk about any type of redox reaction, generally we use a particular medium. Medium can be your acid, aqueous solution of acid, or aqueous solution of a particular base. Always remember, in that particular case, acid contains H positive, your base contains OH negative, and aqueous solution means water is always there. So these three ions are not going to change anything. These three ions are not going to change anything. So either you have H positive, or you have OH negative, or you have H2O, which are basically due to medium, due to the presence of a particular medium. These are not going to hamper any redox reaction, and these ions are actually known as spectator ions. These ions are known as spectator ions. They are going to simply look what is happening in the reaction. They are going to provide required things, but they are not going to hamper anything in the oxidation or reduction process. Okay, so these are known as spectator ions. Okay, now add water molecules. Now first of all, you have to understand that either we have the acidic medium or we have the basic medium. Let's say we have the acidic medium. Let's say we have the acidic medium. So whenever you see that there is acidic medium in the reaction, just look at the side, either left hand side or right hand side, which is deficient in water or deficient in oxygen. If that side is deficient in oxygen, add a required number of water molecules on that particular side. So add water molecules to the side deficient in oxygen and twice number of H positive to the opposite side, exactly opposite side. This is done in mostly acidic medium and in certain cases of neutral medium. Okay, this process is highly useful. Okay, I hope this part is clear. This is for acidic medium. Okay, now what happens in case of alkaline medium? In alkaline medium, the process is exactly opposite. Just look at the side which is oxygen rich. Try to add same, whatever oxygens are extra there, try to add same number of water molecules and twice number of OH negative on the opposite side. So in case of alkaline medium, for each excess of oxygen, add one water molecule to the same side and twice number of the OH negative on the other side. So this is the thing which you have to do in case of alkaline medium only. Now everything is balanced now. Atoms balanced, oxygen balanced, hydrogen balanced. Now what about the charge? Add electrons to the side deficient in electrons to equalize the charge on both sides. So that part also can be done. And multiply one or both the half reactions by a suitable number so that the number of electrons become equal in both the equations and they get cancelled out. That is the entire idea about the equation. It seems to be like 6-7 steps, but after practicing you will get to know like what you have to do while balancing the equation. Okay, okay. So for example, I am talking about this reaction which is Cr2O7 reacting with oxalate ion and it is converting into Cr3 positive as well as CO2. First of all, I can see that Cr is a +6 in dichromate and it is a +3 in chromate. Now if you look at this entire part, you can see that it is converting from +6 to +3. That is the process of reduction. So you can say that reduction involves Cr2O7 2 negative to Cr3 positive. Definitely the second part will be oxidation. Oxidation will be C2O4 2 negative is converting into CO2. First of all, if I want to balance this equation, I have to balance atoms other than oxygen and hydrogen. So two chromiums are there. I can add two chromium. Done. Now this reaction is basically in acidic medium. I know the rule. I want to balance the oxygen. 7 oxygens are there. What can I do? I can add 7 H2O on the deficient side and twice number of H positive on the opposite side. Means 14 H positive are there. Balancing is done. Now you can see O7, O7, 7 2s are 14H, 14H. Everything is clear. But last part, which is the charge balancing. In this case, you can see 14 positive plus 2 negative. That is 12 positive. But in this side, you can see 3 2s are 6 positive. So 12 positive and 6 positive. So can I add 6 electrons here? Can I add 6 electrons here? So 6 electrons, which is 6 negative, 12 positive means 6 positive and 6 positive. Now it is balanced. Next part, C2O4 2 negative, carbon 2, carbon 2, oxygen 4, oxygen 4, already balanced, already balanced. Now in this case 2 negative is there. So I can add 2 electrons to make it again 2 negative. So charge is also balanced. Now in case you can see there are 6 electrons. In this case you can see there are 2 electrons. So let's say I am multiplying this entire equation with 3 so that it becomes 6 electrons and they both get cancel out, and add these two reactions and add these two reactions. So in this case you can see we have Cr2O7 2 negative plus, next we have 3 C2O4 2 negative plus we have 14 H positive gives us 2 Cr3 positive plus 3 2s are 6 CO2 plus next part, which is 7H2O. 7H2O. Now you can see that we have 2 Cr, 2 Cr. We have 3 2s are 6 carbon, 3 2s are 6 carbon. We have 4 3s are 12, 19. We have 19 oxygen, and that 6 2s are 12. 12 plus 7, 19. So 19, and then we have a 14H, 14H. We have 2 negative, 3 2s are 6, 6 negative, 2 negative, 8 negative, and 14 positive, 8 negative, 14, 6 positive, 3 2s are 6 positive. So reaction is already balanced. Reaction is already balanced. I hope this part is clear. So these are two steps which you have to follow, number 1 and number 2, and that depends upon the type of medium you are using. Okay, just have a look at it. Just have a look at it. Just have a look at it. Okay, now let's talk about the next reaction in alkaline medium. Let's try to figure out what is going to happen in this type of reaction. So we have CrOH thrice plus IO3 negative is converting into I negative plus CrO4 2 negative. So first part is this plus 3. CrOH thrice means chromium is in plus 3. CrO4 2 negative means 6 positive. So this process is oxidation. So I can write oxidation half reaction, which is Cr 3 positive is converting into CrO4 2 negative. Why I am not writing the OH part? Because I have to convert that entire part into ionic equation. Okay, and if I talk about the reduction, that will be IO3 negative to I negative. Okay, now Cr already balanced. Oxygen rich side is 4. In that side, I can add 4 H2O and twice amount of OH. So 8 OH will be there. 8 OH will be there. I hope this part is clear. I hope this part is clear. You can see. Or what can we do? And that will be, let's say, 1H2O, 2OH, 2OH. Oh, yeah, we can do that part also. If you want, we can do that part also. Let's say we have a CrOH thrice, and I'm converting this entire part into CrO4 2 negative. So 3 oxygens are there, 1 oxygen will be there. So you can add 1 H2O. Difference is one oxygen, same number of H2O on that side, and opposite 2OH, 2OH negative. If that works, but let's make it simple according to the rule. Let's make it simple that we are moving according to rule. So we have a Cr3 positive, and finally let's try to combine the reaction, and then we'll find out what is CrO4 2 negative. So in that case, 4 oxygen difference is there. So 4 H2O I have added, and that will be 8 OH negative. Okay. Now in this reaction, you can say that 4 plus 4, 8 oxygen, 8 oxygen, 4 to the 8 hydrogen, 8 hydrogen. Everything is clear. Now last part is balancing of charge. In this case, 8 negative and 3 positive. That will be 8 negative, 3 positive will be 5 negative. 5 negative is there, and in this case only 2 negative is there. 2 negative is there. 2 negative means I am adding 3 negative more. So 3 electrons can be added. So it will become CrO4 2 negative plus 3 negative, 5 negative, and in this case 5 negative, balanced. Now iodine balanced. 3 oxygens are there. 3 oxygens are there. It means I can add 3 H2O. I can add 3 H2O and twice amount of OH on that side, OH negative. So you can say 3 plus 3 oxygen, 6 oxygen, 3 to the 6, 6, balanced. Now in this particular case, you can see that we have 1 negative charge, and in this case 6 and 7 negative. 7 negative means I can add 6 electrons here. I can add 6 electrons here. Now both the reactions, oxidation as well as reduction, are balanced. Now it's time to combine the reaction, but in this case we have only 3 electrons, in this case we have 6 electrons. So I can multiply this entire part with 2, and this becomes 2Cr 3 positive first part plus 8 to the 16 OH negative. Okay, plus next part is IO3 negative plus we have 3 H2O. Okay, again we can remove the next part. Gives us we have 2 CrO4 2 negative plus 4 to the 8 H2O plus we have I negative plus we have 6 OH negative. Now you can see 16 OH are there, 6 OH are there, left with 10 OH. So I can say that will be 10 OH. That will be 10 OH only. So 10 OH negative. Done. Now in this case 3 H2O, in this case 8 H2O. So that will be only 5 H2O. I can say that will be 5 H2O. 5 H2O. Now it's time to combine the entire reaction. We have 2 Cr, 3 positive and 10 OH negative. So I can say that will be, the final equation looks like CrOH thrice, because we have started with CrOH thrice. So 2 CrOH thrice are there. So I have included 6 OH negative. So that should be only 4 OH negative. 4 OH negative plus IO3 negative plus H2O, which are 3 in this particular case. So I can remove this 3H2O, sorry, I can remove this 3H2O from here as well as here, and gives us the final equation, which is a 2CrO4 2 negative plus a 5H2O plus I negative. Can we cross verify? So we have 4 negative, 1 5 negative, 2 2s are 4, 5 negative. Okay, if negative charge is there, 2Cr 2Cr, and we have 1I 1I. Hydrogens are 3 2s are 6 plus 4 10, 5 2s are 10, and oxygens are 5 and 4 2s are 8, 4 2s are 8, 13 oxygen on this side, and we have 3 2s are 6 plus 4 10 plus 3 13. Yes, this is a balanced equation. This is a balanced equation. Now you see the limitation in this particular part. It's a very tedious method. It's a very tedious method that you have to use multiple iterations to balance this equation. So that's why we generally prefer oxidation number method, which requires only 30-second calculation. That's it, and you can balance the same equation within 30 seconds or 1 minute max to max. Okay, so I hope this part is clear. Just have a look at it. Okay, now in case of oxidation number method, what happens in a balanced redox reaction? Total increase in oxidation number must be equal to the total decrease in the oxidation number. This is the only thing which is required in this particular case. This method is applicable to both molecular as well as ionic equations. So there is no need to convert the equation into ionic form and then try to decode that equation, just like the previous case. You can directly start with the equation only. Okay, so that is the beauty of this particular method. But the main thing in that particular case, you should know what is the actual change in oxidation number. This is the only thing which is required in case of this entire part. This is the only thing which is required, which is the change in oxidation number. Change in oxidation number. So that part we are going to discuss after the calculation of a valency factor. Okay, that part can be done if we know what is actually n factor. If we know what is n factor, then entire part will be much more easier for us. So let's try to figure out what is n factor, then we will proceed for the oxidation number method. Okay, so we have one question. What will be the value of x, y and z in the following equation? Very simple type of equation. You can see we have H2C2O4 plus H2O2 is converting into CO2 plus H2O. So in this particular case, you can see that what can we do? What can we do? Either you can convert the entire part into two equal halves, or you can use the hit and trial method that you uses earlier in case of ion, your mole concept, balancing of moles. So that part can be done, and or either you can use the next part. So basically we have C2O4 2 negative, which is converting into CO2 first half, and next part is H2O2 is converting into H2O second half of the reaction. So I have written both the halves. You can try to balance these equations by yourself. Otherwise, what can we do in this case? Plus 3 plus 4 is converting into 1 2. So 2 will be there, and minus 1 minus 2, so 1 will be there. So I can say minus 1 2 minus 2 1 2, so 2 and 2, so nothing will be there. 2 carbons, so I can say that will be 2 carbons, and uh, let's figure out the next part. 4 oxygens, so I can say that will be y will be 2, y will be 2. So this is out of the equation. This is out of the equation. Okay, so we have 2 2 1 or 1 2 2. So if that is 1 2 and 2, so that will be, sorry, 1 2 and 2. So 2 oxygens are there. 2 to the 4 plus 2 6. 2 plus 4 6. So that will be 1 2 2. That will be 1 2 2. Okay, that will be 1 2 2. but you can solve the equation by yourself. I have like directly solved the equation by hit and trial method, but I have written both the equations. This one is the oxidation half and this one is the reduction half reaction. So try to balance these equations, whatever I have given you the data, and try to solve what is going to happen. Definitely it's the acid. H2C2O4 is oxalic acid, so medium will be acidic. So this is happening in acidic medium. Okay, try to balance this equation. Okay, if you are like little bit confused, then I can help you with that part. So two carbons are there, it means 2 CO2, 2 2s are 4, 2 2s are 4, everything is already balanced, but the only thing is two negative charges are there, so two electrons are there. H2O2 is converting into H2O. It means in this particular case you can see that this side is oxygen deficient, so I can add 2H2O and twice amount of H positive, so that will do, I guess. So two oxygens, two oxygen, 2 2s are 4, 2 2s are 4 hydrogens, but 2 positive is there but neutral is there, so you can add 2 electrons here. So 2 electron, there is no need. So what you can do, you can do 2H positive plus a C2O4 2 negative plus H2O2, okay, gives you 2CO2 plus 2H2O, and 2 electrons are getting cancelled. 2H positive plus C2O4 2 negative is H2C2O4. So you can rewrite this equation, which is H2C2O4 plus H2O2 gives us 2CO2 plus 2H2O. So this X will be 1, this will be 2, and this will be 2. So 1 2 2. Okay, that's how you can deal with this equation. Very simple analysis, very easy analysis. Okay, so the next thing which is important is what is N factor and how to calculate that entire part. So to understand the N factor, now the entire chapter, trust me, the entire chapter of this redox reaction actually depends upon the calculation of N factor. If you know how to calculate the N factor, then entire part is going to be very easy. So the next part is basically related to the origin of N factor and how to calculate N factor for different type of components, whatever we are using, either acid or base, whatever it is. Let's try to figure out what is going to happen. Okay, so for that part we have to understand the concept of equivalence. Okay, we have to understand what is the concept of equivalence. What happens if I talk about the classical method? So the classical concept of equivalence was very lame. It was actually very lame. So if you know that if I talk about the concept of molar mass, so molar mass is basically the mass of 1 mole of a species, any type of a species. That is the basic definition of a molar mass. Just like that, we have another term. This is represented by capital M. We have equivalent weight. Just like that, we have another term which is equivalent weight. And how you are going to define that particular part? So this equivalent weight was initially started or initially calculated for elements only. For elements only. Okay, initially it was started for elements only, but now it's a very wide concept. You can use that concept for any type of reaction. So in that case, the equivalent weight of a particular element is that weight of the element that will either going to combine or replace directly or indirectly 1 gram of hydrogen, 35.5 gram of chlorine and 8 gram of oxygen gas, or 108 gram of silver. That is the basic idea. For example, let's talk about the analysis in that particular case. Let's talk about the analysis that I have zinc. I am reacting it with H2SO4. Zinc granules, when added in H2SO4, generally a reaction takes place and it converts ZnSO4 as well as liberates H2. This reaction is a balanced reaction. If you see, this reaction is basically balanced chemical equation. Done, no issues. Now if you see that 1 mole of Zn actually liberates 1 mole of H2 or hydrogen gas, or 1 mole of hydrogen gas. Okay. Okay, 1 mole of hydrogen gas. I hope this part is clear. I can say 1 mole means 65 gram of zinc liberates 1 mole of hydrogen gas means 2 gram. 2 gram of H2 gas, hydrogen gas. Okay, from this calculation. Can I say that 1 gram of H2 gas will be displaced by 65 by 2 gram of zinc? Can I say if 2 gram is displaced by 65 gram, then 1 gram will be displaced by 65 by 2. I'm not solving this. I'm not solving this. Let's say next part. Let's say next part that Mg reacts with oxygen to form MgO. This reaction is balanced equation? No, this is not a balanced equation. So I can multiply 2 here and 2 here. Now it becomes balanced chemical equation. So that we can apply mole-mole analysis. I can say that 1 mole of oxygen gas actually reacts with 2 moles of magnesium. It can react with 2 moles of magnesium, definitely. Or I can say 1 mole means 32 gram of oxygen gas actually reacts with 2 mole of magnesium. So magnesium 2 moles means 2 multiplied by 24 gram of magnesium. Okay, done. According to definition, we have to pick 8 gram of oxygen. So 8 gram of oxygen gas will react with 2 multiplied by 24 divided by 32 multiplied by 8 gram of oxygen, sorry, of magnesium. Abhi you can calculate for 1 gram, na? For 1 gram that will be 2 multiplied by 24 divided by 32. So for 8 gram that will be multiplied by 8. So you can say this will be 4 and this will be 2. So that will be 24 divided by 2 gram of magnesium. You must be thinking why I am not solving this entire part. I am using the calculation but I am not solving. Let's try to figure out one more thing. Last thing, only last thing. So let's say that aluminium reacts with chlorine gas to form AlCl3. Is this a balanced chemical equation? No, it's not. So you can calculate that will be, let's say I am using 2 here, so that will be 3 here and 2 here. Now this is the balanced chemical equation. You can see this is a balanced chemical equation. Just see, 2 aluminum, 6 chlorine and 6 chlorine, balanced chemical equation. You can say that 2 moles of a chlorine gas actually reacts with 2 moles of aluminium. Can you see? Yes, definitely that is for true. Or I can say if 2 moles of sorry that should be 3 moles of chlorine. 3 moles of chlorine actually reacts with 2 moles of aluminium. 3 moles of chlorine, if you want to convert, that should be 3 multiplied by 71 gram of chlorine actually reacts with 2 mole of aluminium, which is 2 multiplied by its molar mass, that is 27. 27 is the molar mass of aluminium. Gram of aluminium. Done. Okay. Now according to definition that should be 35.5. So I can say that 35.5 gram of chlorine gas will require 2 multiplied by 27 divided by 3 multiplied by 71 multiplied by 35.5 gram of aluminium. So that will be 35.5 twice. This is going to be cancelled out. So that should be 27 divided by 3 gram of aluminium. Now what I'm trying to say in this particular case, if you see that I'm using the reaction of Zn plus H2SO4 gives us ZnSO4 plus H2. For 1 gram of hydrogen gas, it requires 65 by 2 gram of zinc according to definition. In second reaction, which is 2 mg plus O2 gives us 2 mgO. 8 gram of oxygen gas will require 24 divided by 2 gram magnesium. In the third scenario, 3Al plus 2Al plus 3Cl2 gives us 2AlCl3. In this case, 35.5 gram of Cl2 gas required 27 by 3 gram of aluminium. Now, if I ask you what is the molar mass of zinc, you can say 65. If I say what is the molar mass of magnesium, you can say 24. If I say what is the molar mass of aluminum, you can say 27. Now, in every case, you can see that the molar mass every time is divided by a specific number. This entire molar mass is divided by the specific number, and that gives us the value of E, which is nothing but equivalent weight. So, according to the definition of equivalent weight, basically when the molar mass is divided by a specific number, that number can be anything. It can be 2, it can be 2, it can be 3, depending upon the type of reaction you are using. So, when this molar mass is divided by the a specific number, then we get the value of equivalent weight. That's why always remember that equivalent weight will be equal to the molar mass divided by a specific number, which is known as n factor, which is actually known as n factor, and this n factor is also known as the valency factor. This n factor is also known as valency factor. Okay, I hope this part is clear. I hope this portion is clear to everyone. That is the basic idea about the n factor. That's the basic idea about the n factor, or known as valency factor. Now, always remember one thing, that n factor, first of all, can be in a fraction, can be can be a positive number, can be a negative number, because we need only the number. We only need the number. So, it can be positive, it can be negative, it can be in a fraction. So, nothing to worry about. But n factor is always calculated for 1 mole of species. This part always calculated for 1 mole of the species. Now, this part is true for these type of calculations which are related to the proper definition of elements. But always remember that you can calculate n factor. N factor can be calculated for acids, bases, salts, cations, anions, oxidizing agent, reducing agent. You can calculate for any type of species, which can be acid, base, salt, cation, anion, oxidizing agent, as well as reducing agent. So, you can calculate n factor for any of the species. In that case, n factor is basically change in oxidation state multiplied by number of atoms of that element in 1 mole of species. Okay, so that's the only thing. First of all, what is the change in the oxidation state of that particular element multiplied by the number of atoms of that element in 1 mole of the species. If you know this thing, that entire part of n factor is going to be very, very, very easy. Okay, I hope this part is clear. I hope this entire part is clear. It is independent of stoichiometry, always remember. It is independent of stoichiometry. There will be no effect on stoichiometry. But in 1 mole, if 2 atoms or 3 atoms are there, you have to include that part. So this is the only thing which you need to be very careful. Okay, I hope this entire portion is clear. That is the basic idea about the equivalents, the origin of equivalents, as well as the idea about the n factor. I hope this portion is clear. I hope this portion is clear. Okay, now if I talk about the equivalent weight, then I can simply define equivalent weight for any type of species, that is the molar mass of that species divided by a specific number which is known as n factor. So equivalent weight of an element can also be calculated with the help of the n factor or valency factor. So you can say equivalent weight will be molar mass of that particular element divided by its n factor or valency factor. That's it. That's it. And you can calculate this entire part for different type of species. So E will be equal to m by n factor. And n factor can vary. N factor can vary depending upon the type of reaction, but always remember it is calculated for 1 mole of that particular species. In the same way, if I talk about the equivalent weight of compound, so whatever the formula mass of compound is, molar mass definitely, divided by n factor, divided by n factor. For oxidizing as well as reducing agents, molar mass divided by the number of moles of electrons gained or lost, because that will be the n factor. That will be the n factor. Okay. That will be the n factor. Now the next part is the calculation of n factor. For example, let's talk about the n factor. Let's take very simple example. First of all, let's take very simple example that we have H2S and it is converting into sulfur, and you can calculate n factor for forward and backward reaction, and both are going to be different. So this is the thing which is happening. Very simple example. You know, in this particular case, the charge is -2, this part is 0. If you calculate the n factor here of sulfur, n factor of sulfur only, n factor of sulfur only. So change in oxidation state is 2. How many atoms of sulfur are there? 1. So n factor will be 2 in this case. N factor will be 2 in this case. Let's say I have a Cr2O7, 2 negative. It is converting into Cr3 positive. So if I talk about the n factor of chromium, that will be +6 to +3. Change is of 3 multiplied by 2 atoms of chromium are there in 1 mole. So that will be 6. Okay, that will be 6. If I say that I have MnO4 negative, it is converting into MnO2. So Mn is in +7, it is in +4. N factor of Mn will be change 7 to 4 is of 3 multiplied by 1. So n factor will be 3 in this particular case, and that's how you can deal with the n factor calculation. Okay, for example, that we have Na2S2, let's say we have Na2S2O3 and it is converting into Na2S4O6. Interesting case. So in this case, if we calculate, always remember, whenever we calculate the oxidation number or change in the oxidation number or n factor, you don't have to talk about the individual oxidation state. You can talk about the average part. So in the average calculation, we know this part is +2 and this part is +2.5. We have already calculated that part in the previous class, if you remember. So from +2 to +5, if I talk about the n factor of sulfur, that will be changes of 0.5 only, and 2 atoms are there of sulfur, so that will be equal to 1. So these are the things which you have to understand. Okay, next part is, let's say So let's say IO3 negative is converting into I negative. So IO3 negative means plus 5 and it is converting into minus 1. So N factor for iodine will be equal to plus 5 to minus 1, changes of 6. 6 multiplied by only one atom is there. So that will be 6 only. Okay. For example, S2O3 2 negative is converting into SO4 2 negative. Okay. S2O3 2 negative means 2x minus 6 will be equal to minus 2. That will be plus 2. So plus 2 is converting into plus 6. I'm directly using it. So in this case, if you want to calculate the N factor for sulfur, that will be plus 2 to plus 6, changes of 4, and 2 sulfur atoms are there. So you can say that will be equal to 8. I hope this entire part is clear. I hope this entire part is clear. There are some special cases also. There are some special cases. For example, that I have FeS2 is converting into Fe 3 positive plus SO2. Let's say it's a very good example. It's a very interesting example. So in this particular case, first of all, you have to calculate what is the oxidation state of iron and sulfur. So FeS2 is a combination of actually Fe2 positive as well as S2 2 negative. Okay. S2 2 negative means sulfur is in minus 1 and this one is in plus 2. This one is in plus 2. And it is converting from plus 2 to plus 3. And sulfur is converting from minus 1 to plus 4. Means you can say that Fe is oxidizing as well as sulfur is oxidizing. If both species are oxidizing, in that case their N factor is calculated. If both species are oxidizing and both species are reducing, in that case total N factor will be N1 plus N2, whatever N factors are there. Okay. So if I want to calculate the first part, N1 in this case for iron, plus 2 to plus 3, changes of 1 and only one iron atom is there. So that is 1. N2, sulfur is converting from minus 1 to plus 4, changes of 5 and 2 sulfur atoms are there. So that will be 10. So N total will be 11 in this particular case. Okay. It's a very good example. It's a very good example. I hope this part is clear. Just have a look at it. Just have a look at it. Okay. There might be a chance that we have another part. Let's say okay, FeC2O4 is converting into Fe3 positive plus CO2. Same type of example. In this particular case, you can say that C2O4 is a 2 negative because it's a combination of Fe2 positive and C2O4 2 negative. Oxalate ion is there. So N1 will be plus 2 to plus 3, 1 multiplied by 1, that will be 1. N2 will be C2O4 2 negative, carbon is present in plus 3 and it is converted into plus 4. So changes of 1 but 2 atoms are there. So that will be equal to 2. So N total in that case will be 3. Okay. Both species are oxidized or reduced. Their N factor will be added together. There might be a chance that one species is oxidizing, another species is reducing. Let's say NH4 twice Cr2O7 is converting into N2 plus Cr2O3 plus 4H2O. That is the reaction. Okay. So one species is oxidizing, another is reducing. So you can calculate the N factor for nitrogen, because nitrogen is present in -3 and it is converting into 0. So you can calculate N factor for nitrogen. So in that case, -3 to 0, changes of 3 and 2 atoms of nitrogen are there. So that will be 6. Now you can calculate N factor for chromium, because in case of chromium it is in +6 and converting into +3. So you can see again changes of 3 and 2 atoms are there. Now you see both the things are same. So in this particular case, in a given compound, if one atom is oxidized, one atom is basically reduced, then in that case N factor, total N factor will be the N factor for the reduction. N factor for the, although both are going to be equal, but you can consider only reduction part. Okay, so in this case a total N factor will be 6 only, will be 6 only. So one species in both are oxidized and both are reduced, you have to add. In one species where one compound, one element is oxidized, one is reduced, so then consider only reduction one. Now the last part, the interesting one, which is disproportionation. So in case of disproportionation reaction, how you are going to calculate that part? How you are going to calculate that particular part? It's again very easy. So let's say I'm talking about the reaction which is the Cl2 plus OH negative is converting into Cl negative plus ClO negative. Let's say this is the reaction. Now in this case you can see that from 0 to -1 and from 0 to +1. From 0 to -1, from 0 to +1. So total N factor. You can calculate the N factor for oxidation. Calculate 0 to +1, changes of 1, 2 atoms are there. So 1 multiplied by 2, that will be 2. You can calculate N factor for reduction. That will be 0 to -1, changes of 1 multiplied by 2, that will be 2 only. So let's say this is N1 and this is N2. This is N2. In the case of disproportionation reaction, always remember that 1 upon N factor total will be equal to 1 upon N1 plus 1 upon N2. Always remember that is the entire case. So if I calculate for this particular part, I can say 1 upon N factor total will be equal to 1 upon 2 plus 1 upon 2. That will be 1. So N factor total in that case will be 1 only. Okay, I hope this part is clear. You can do that part for same reaction, which is H2O2 is converting into H2O plus O2, let's say. So in this case N1 will be -1 to -2. So 1 and 2 atoms of oxygen are there, so that will be 2. N2 will be -1 to 0. Again changes of 1 multiplied by 2 atoms, that will be 2 again. So again in this case N factor, which is total, will be 1. That is 1 upon N factor total will be 1 upon N1 plus 1 upon N2. I hope this entire part is clear. I hope this entire part is clear. Now if I talk about the oxidation number method, it's going to be very, very easy. If I talk about the oxidation number method, this is going to be very, very easy part. Literally very easy part. You just have to calculate the N factor. So what you have to do? First step, calculate N factor of oxidizing agent and reducing agent and cross multiply them in left side, only left side, which is the reactant side only. Okay, then second part, try to, or rest of the part is AOHC. Rest of the part is AOHC, depending on the medium. depending on the medium. That's it. So let's talk about the same equations which we tried to solve for first part, which is Cr2O7 2 negative plus C2O4 2 negative. So in this case, let's say we have the same equation. Okay. So we have Cr2O7 2 negative plus a C2O4 2 negative gives us Cr3 positive plus CO2. Let's say this is the reaction. So I can calculate the N1 here. Cr is basically plus 6 here and is converting into plus 3. So plus 6 to plus 3, changes of 3 multiplied by 2 chromium are there. So basically that will be 6. Next part, C2O4. So N2 will be plus 3 to plus 4. Changes of 1 and 2 atoms are there. So 1 multiplied by 2, that will be 2. So either you can cross multiply 2 here or 6 here, or you can take minimum ratio. Minimum ratio is 6 is to 2 or 3 is to 1. So 3 is here, 1 is here. So I can cross multiply 1 here and 3 here on the reactant side. Now 2 Cr are there. So 2 Cr. 3 2s are 6 carbon, 6 carbon. Now medium is acidic already given. Medium is acidic already given in the equation. In this case, we have 4 3s are 12. 12 oxygens and 7 oxygen. 19 oxygens are there. But in this case, 6 2s are 12. So 7 oxygens are remaining. So 7 H2O on this side plus twice number of H positive, 14 H positive. Balanced. Tada. You can see balanced equation. So this is the basic idea about the entire analysis of the reactions which which involves the oxidation number method. It's very easy to deal with the oxidation number method. Now let's talk about the second reaction which we were doing. That was, I guess, IO3 negative plus, I'm not sure about the reaction. Let's find out. Because okay, so that was CrOH thrice plus IO3 negative gives us I negative plus CrO4 2 negative. So that is IO3 negative plus CrOH thrice gives us I negative plus CrO4 2 negative. That was the reaction. Can we calculate the N1 here? So this is plus 5 converting into minus 1. Plus 5 to minus 1 is change of 6. Okay, 1 atom. So that will be 6 only. N2 will be equal to plus 3 to plus 6. So 3 multiplied by 1, that will be 3 only. So I can cross multiply either 6 here or 3 here, or minimum ratio. 6 is to 3 is 2 is to 1. So I can multiply 2 here, 1 here. So 1I balanced. 2 Cr, 2 Cr. Now in this case, I can say that we have 3 2s are 6 plus 3 9 and 2 4s are 8. So I can add 1 H2O and 2 OH negative on that side. So no, oh, okay. Same mistake. So the equation was supposed to be IO3 negative plus Cr3 positive. Sorry, same mistake. Gives us I negative plus CrO4 2 negative. That was supposed to be the reaction. Now in this case, we have calculated N1 was 6, N2 was 3. So I can multiply 1 here and 2 here. Now in this case, 2 will be there. Now you see this side we have oxygen which is 3. This side 4 2s are 8. So difference is of 5. So I can say that 5 H2O I have added here on the rich side, and I have added 10 OH negative on this side. reaction is balanced. Reaction is already balanced. So you can see like only single step is required in this type of reaction. So everything is already balanced. You can see 2Cr, 2Cr, I10 oxygen and 13 oxygens are there. 10 and no, I guess this must be 4 2s are 8. 8 and 3. So 5H2O, 10 OH. So 4 2s are 8 plus 5, 13. 13 here, balanced. 10 hydrogen, 10 hydrogen, balanced. And negative charge, you can see that 10 negative, 1 negative, 11 negative, and 6 positive. 6 positive means 5 negative, and 2 2s are 4 and 5. Already balanced, already balanced. So you can see it's better to use oxidation number method whenever you are dealing with the balancing part. So, okay. So one thing I may suggest you, because in NCERT there are different questions for the balancing part. If you have module, so a very simple homework that will give you a boost that how to deal with the balancing part. Try to solve at least 20 to 25 questions on balancing with only oxidation number method. With only oxidation number method, you can prefer PW module. If you have PW module, you can prefer to that particular part. If you have a specific book, then you can go go through that book and try to solve at least 20 to 25 questions depending upon the balancing, so that you get the idea how to calculate the n factor, how to deal with the balancing part. That will be much more easier. Now in next part of this session, we are going to talk about the last portion, which is nothing but the concept of law of chemical equivalence, extended version of n factor for acid base different type of reactions, normality. That part is very easy, and remaining part is titration only. Okay, so that part we are going to discuss in the next class. Okay, so I hope everyone enjoyed this session and learned something new from this session. Always remember one thing, that the equivalent weight of any of the compound or any of the species is basically molar mass of that species divided by its n factor. And n factor can be anything. It can be anything. Generally, in case of elements, always remember, first of all, in case of elements, it's the valency. Second case, in case of your oxidizing as well as reducing agent, that is the number of electrons lost or gained by 1 mole of that species. If I talk about the species which is, let's say, how can we say, cations or anions, that will be the actual charge of that cation and anion, and that's how you can calculate the n factor and divide the n factor with molar mass. So that's all. Okay, so the remaining part of this session we are going to discuss in the next class. So that's all from my side. Thank you so much.